with a bit more of an understanding for how matrix multiplication works, we're now going to move into section 8.4, where we're going to talk about some important constructions within matrix multiplication, a couple of very important types of matrices that we can talk about. And I'll say that for this section, we are going to pretty much entirely focus on square matrices. That is, ones where the number of rows equals the number of columns, n by n matrices, for reasons that will make sense as we're going. But the first thing we're going to look at here is something that behaves like an identity. So when it comes to multiplication of numbers, we have the very basic identity there that if you multiply something by 1, it essentially doesn't do anything. And we saw when we were talking about scalar multiplication that that kind of works too for matrices. If you multiply a matrix by the number 1, you just get the matrix. And that's fine, but is there more we can do? Is there something we can do with another matrix where if we multiply it by something, nothing changes? And to get there, let's think about something in terms of 2 by 2 matrices, because those are relatively nice to work with, and for reasons that should become clear soon, we need it to be square. So let's say we have a general 2 by 2 matrix like this with elements A, B, C, D. That is, they can be anything we need, because we're trying to be as broad as possible. So let's take that A, B, C, D. And our goal is to multiply it by something in a matrix form and get back the exact same A, B, C, D. We want nothing to change. Well, for one, it has to have the same number of rows as this does columns. So it has to be 2 by something, just like this one is. And if we need it to have the same order, because it has to get back to the exact same thing, it also needs to have the same number of columns as this one does rows. So it also needs to be 2 by 2. And when we're thinking about our first term, this thing that's going to go up here, we're talking about multiplying this times something in there in that first column. And in that first column, we would need A times something plus B times something. Oh, can't give it away just yet. To come out to just be A. Because remember, when we're looking at matrix multiplication, to get this guy right here, we need this combined with that. Well, if we need the B term to go away, like I spoiled, that has to be 0. And if we need the A term to stay, that has to be 1. So no matter what else happens, in order to get A right here and nothing else, we need 1, 0. And then let's do the same sort of thing to get this term down here. For that term down there, we take second row, second column. So C times blank plus D times blank. And I'm not going to spoil it this time, but hopefully you can guess something like what's going to happen, because this needs to equal D now. We need to get that guy there by itself. Well, we've got to get rid of C, we've got to keep D. So that has to be 0. And that can't be anything other than 1. So just by looking at these two terms having to end up back where they started, and our matrix having to maintain order, we get that in order for this to happen, in order to multiply these two and end up back where we started, that has to be our construction. And this is a very particular construction. This is something that's often notated I sub 2, and it's what's called the identity matrix. of order 2, where it has this form and a little bit of a nicer setting. And when we're looking at I2, we can take A times I2 or I2 times A, and we'll still just get A. And I'm not going to go through the steps of it because it gets more complicated as you go further, but it essentially always works this way. Where, in general, if we want something more complicated, something of order n, it will always end up taking this form. The identity matrix of order n will have 1s along the diagonal and 0s elsewhere. And yeah, there's going to be a few more 0s in here, but, well, I think at this point, you get the picture. That what we're looking at, diagonal of 1s, and a whole great big pile of 0s. But hopefully, this leads to another question. Because if we think about this guy over here, we remember that the idea of a identity by multiplication indirectly implies an inverse. As if you want to get 1, you can multiply A times the inverse of A, or the inverse of A times A, where usually for numbers we write that as 1 over A. So, would it make sense that as a result we can take some A of order n, multiply it by some inverse of order n, and get back the identity of order n? And the answer we'll see to that question is, unfortunately, sometimes. But that's what we'll see next, is the idea of the multiplicative inverse of a matrix.